So now we really want to get into some of these properties of logarithms. So we saw properties of exponents. So we're going to have a lot of those same properties now with logarithms. So one that really we didn't see with exponents, but is probably one of the most important of the logarithm properties is what's known as the change of base formula. Okay. So first, let's start, before I get into what the actual formula is, let's revisit the initial question that we started this whole unit with, which was what's 2 to the x? If 2 to the x equals 5, then what is x? Okay. And we mentioned that we would need a logarithm to solve this. Specifically, now we can see that this is going to be log base 2 of 5. Okay. But this still doesn't help us too much because we don't know how to solve this by hand. If you go to the calculator and you try to look for how to input this, you might be confused as well. Because usually they only give you log base 10 or log base e, the natural log. So what do we do, right? How do we fix this? And you might notice on a calculator that you're not able to input a base for the logarithm manually on most calculators. And that's because we don't need to with the change of base formula. Okay. So the change of base formula is exactly what it sounds like. It lets us change the base of the logarithm. So if we have log base b of a, then this is equal to log of a divided by log of b. Now notice that I didn't write the base of the logarithm on the right side. This is because the base doesn't matter. It can be any base. So this is what we mean by the change of base formula. We're able to take this logarithm which has base b and turn it into a quotient of logarithms with any base we want. Okay, so this will allow us to put a number in the calculator, for instance, or of course it'll have other uses as well. So we can do log base 2 of 5 is equal to log of 5 divided by log of 2. So now you can actually find out what that is just by throwing it in your calculator. Okay. Okay, so next let's go through some of these properties one by one here. So first of all, a couple that don't really have a name, and you can debate whether they're actually like properties. But something like this, so the logarithm of 1, it doesn't matter what the base is, this is always going to be 0. So again, not really like a property, but just something that's helpful to remember. And this is just because you're saying b to what power equals 1, and we saw in the exponent properties, the 0 exponent rule, that this is going to be 0. Okay, so the inverse of that is that the logarithm of 1, no matter what your base is going to be 0. Okay. Similarly, log base b of b is always going to be 1, because again, you're saying b to what power equals b, so that's always going to be 1. And for all of these, we have the same restrictions on b as we did before, so I'm not going to write them out every time, but b has to be non-zero, greater than 0, and not 1. Okay, so next one, which is very useful, is the inverse property. Okay. So this says there's 2 parts to this one, that log base b of b to the x is equal to x. Okay. Again, we can see this just by flipping the logarithm around, right? If we say b to what is equal to b to the x, well, the answer just kind of falls out there, right? It's just x. So instead, if you're since we're already using x, maybe we say b to what power is equal to b to the x. Well, this is going to be x, of course, right? If you have two of the same base, to get that equality, they got to be raised to the same number. This actually is a consequence of the fact that the exponential function is 1-to-1, or invertible. Okay. And then on the other hand, if we write it a different way, see that b to the log base b of x is equal to x. So this one's a little bit weird. Now the logarithm is in the exponent. So if we wanted to show that this was true, maybe we start with like b to the log base b of x, and we say, okay, we don't know what this is, so let's say it's equal to y, and then we're going to flip this around into a logarithm, and we say, okay, this is log base b of y equals log base b of x, and this is going to imply that y is equal to x. Okay. This actually is also a property, a consequence of the fact that the logarithm is 1-to-1. Okay. So you can show that the logarithm is 1-to-1 as well. So it's kind of already been implied that it's 1-to-1 because it's defined as the inverse of the exponential function, and in order for something to have an inverse, it has to be 1-to-1. So I think it's okay to just use that without showing it. But anyway, so this shows us this property, and this is really useful. One thing to note is that it has to be just the logarithm by itself, okay? So if we have something like 4 to the 2 times log base 4 of x, this is not equal to x, okay? It needs to just be 4 to the log base 4 of x, okay? This would be equal to x. So these kind of cancel out. So something like this we'll be able to handle it by the end of this video, once we look at a different property. Next up is the product rule. First property we looked at for exponents. So the product rule, sometimes it's called the product rule for logs or logarithms. Okay. But it's actually just a consequence of the product rule for exponents. So the product rule for logarithms, I'll just show what it is first, and then we can go ahead and prove that it's true. So log base b of m times n is equal to log base b of m plus log base b of n. So pretty much the same flow as the exponential product rule. When you have two things being multiplied with the same base, you break them up over addition. Okay. So I'll just do a quick proof just to show that these are true. Of course, we're mostly mostly concerned about using it rather than, proving it right now. But I think it's helpful just to see where these things come from, right? So let let m equal log base b of m, and n equal log base b of n. Okay, so these are terms on the right hand side of the equation. Then this of course is going to imply that then b to the m equals m and b to the n equals n. Okay, so log base b of m times n, this is going to be equal to log base b of b to the m times b to the n, right? Just based on what we just defined up here. So now we can use the product rule for exponents. say this is log base b of b to the m plus n. Okay. Now we can use the inverse property for logs that we just defined a second ago to say, okay, this is m plus n. And now, just using what we just defined a second ago, this is log base b of m plus log base b of n. Okay. And then we're done. Okay. So we're really just using the product rule for exponents here. And then just the definition of a logarithm. Okay. All right. So, and we're just going to look at all the rules now, and we'll have a separate video where we actually start applying these and looking at these in equations. Okay. And of course, this works with more than one thing too, just like with, or more than a pair of things, right? You could have 3 things in the inside and you can break them all up over addition. Okay. Now the quotient rule. Okay. So I won't prove this because it's the exact same proof as what we just did, just using the quotient rule in place of the product rule. So this is log base b of m divided by n is equal to log base b of m minus log base b of n. Okay. So now with quotients, you can break them up over subtraction. So actually, I would encourage you, just using the proof that I just did up here for this one, maybe go ahead and try proving this one in the same way. Because like I said, it's the same flow. It's just using the quotient rule where you use the product rule here. So maybe that's a good thing to do for practice. Okay. So both of these will allow us to simplify logarithms quite a bit, as we'll see when we start looking at equations that involve logarithms. Okay. Another one that is extremely useful for logarithms is the power rule. Okay. So this says that if we have log base b of, let's start with a specific example rather than writing out the actual rule. A little bit specific, right? We're still not specifying the base, but we're saying log base b of x squared. Okay. Then this is equal to log base b of x times x, of course. That's just the definition of exponents. And now using the product rule for logarithms, this is log base b of x plus log base b of x, which is 2 log base b of x. Okay. So ultimately, log base b of x squared is equal to 2 log base b of x. So what happens here is that this inside part, this part right here with the product rule for logs, if you have, say, log base b of a to the n, here there's going to be n copies of that. So this is going to be equal to n log base b of a. Okay. So that exponent kind of comes out in front. Okay. So this would be the power rule for logs. Okay. So this is a really useful property. You could actually go back and reprove the quotient property using this property, or a lot of the properties we've already looked at using this property, like the inverse property, for example. So this one is very useful. Actually, we can come back now to the one that I said we'd be able to do by the end of this video. I believe it was this, right? Now we can do this because we can see that, okay, this logarithm that's in the exponent, that's the same thing as log base 4 of x squared, right? It works the other way too. And now we have 4 to the log base 4. Those cancel, and we're left with x squared. Okay. So we can combine the power rule with the inverse property in order to ultimately solve this problem. Okay, so just one quick example of just something that uses a lot of these. So we'll see these a lot when we're solving equations with logarithms in them. Okay, so what if we just have something like log of x squared times y cubed divided by z to the fourth? Okay, so first we expand it out with our product rule and our quotient rule minus log of z to the fourth. Okay, so we just write it all in a row like this. So the first part's from the product rule, and then the minus part is from the quotient rule. And then we use the power rule to bring all the exponents out front. So we get 2 log of x plus 3 log of y minus 4 log of z. Okay, so this is just kind of, the way that it's used to make the expression a lot simpler. Here now we just have the log of something, some numbers, and then we see we have 2 copies of the first one, 3 of the second one, 4 of the third one. The log of something is something that we could just quickly put in the calculator. So it'll allow us to make the expressions a lot simpler. And maybe it would actually be simpler by going the other way. Maybe instead of expanding out, the problem would be simpler by condensing the expression. And we could do that too. Okay. So an example of that, maybe we have log of 3 minus log of 4 plus log of 5 minus log of 6. So we're stuck with all these logarithms, and we think, okay, well, maybe we could just condense these into one expression just to make things simpler. Okay, I'll take it in 2 steps here. First, we'll do the first 2. So using the quotient rule, this is log of 3/4. And then the second 2, this is log of 5/6. Okay. And then using the product rule, this will be log of 3/4 times 5/6. So 15 over 24. And then we get it all just in one nice condensed expression.